Hi guys, and welcome to today's YouTube video course. In today's course, we will see the heap memory allocation in embedded systems. First of all, we'll start by covering the different steps needed to set up our STM32 based project. This microcontroller-based project will be needed to demonstrate the different concept and theory that we are going to learn across those different slides. All of that will be running on a real hardware microcontroller device. We'll start first of all by defining the heap memory concept itself. So we'll explain for what the heap is used and how it gets allocated within our C-based program. Allocation, this is done via a set of APIs and functions that we're gonna try to cover within this section. Then we'll see how we can initially allocate the heap memory segment through our embedded system based project. We will focus here more on how we can configure and set up our Linker script to reserve a memory segment dedicated for our heap memory. We will see as well the different pros and cons of heap memory user. And finally, we will see a live example that will be running on an STM32 microcontroller to demonstrate how we can allocate heap memory segment. The hardware to be used will be an STM32L4 Nucleo port. The project tools, they're gonna be located under Wadix Technology Tools GitHub repository. And the C-based project will be located as well under Wadix Technology Courses GitHub repository. The different links will be provided as part of those slides, and of course the link to the location of those slides will be within the YouTube description. We'll need now to clone and check out our Wadix Tools GitHub repository under C drive. My recommendation is to pick up C drive because it offers short paths to the different tools and applications to be used out of our tools directory. Now, in terms of tooling, our Wadix Tools GitHub repository offer quite big number on terms of toolings and applications. Nevertheless, for our makefile based project, we will need mainly the ARM GCC compiler. This is the ARM non-EOB GCC compiler from ARM, and this is targeting mainly the ARM Cortex-M microprocessors family. Our makefile project will be an ARM Cortex-M3 based project. Then we'll need this GNU Win32. This one does contain already our GNU Make Build tool. And finally, we'll need set of tools and applications to be used in combination with our make file. So those applications will be used as part of our makefile rules to create directories, remove directories, copy files, change or modify existing files, and so on. Cgwin64 does provide those set of applications. Example, we can create directory via this mkdir application. we can remove via rm as well as rmdir for directories and so on. Now we'll need to set up our Windows environment variable path to point to those applications and tools. Hence, the Windows system will be able to recognize the location of those tools and applications once they get invoked via the command line. For that, I have prepared this PowerShell script install environment. Once executed from a PowerShell session, then the Windows environment variables for the current account will be updated to point to our applications and tools needed by our project. If you want to revert back, then you can use this an installation environment PowerShell script. So this to install, and this is to restore back the old paths. To execute those scripts, you need first of all to open a PowerShell session. So like this, as you can see. Then the first thing to be done within the current active PowerShell session is to enable the execution policy. This one enables PowerShell to accept external scripts and execute them. Without running this command, the PowerShell session will block the execution of our PowerShell installation script. Once we executed this set execution policy, we can navigate to our tools directory. Then we initiate the execution of our installation PowerShell script. Once done, the Windows environment variable path will be updated and pointing to our applications. So if we inspect the environment variable of our account, then we go to path. As you can see, the path has been updated to point to our Segment64 applications as well as make build tool as well as the ARM GCC compiler. If you want to revert back, then you can just execute the uninstall PowerShell script. Now if we inspect again, as you can see, the previously added tools has been removed. Now I will just execute again this install PowerShell to be able to move forward within our makefile based project. As you can see, this has been added again. Now we can move forward and check out our makefile based project. On embedded systems, heap memory is just a memory segment that can be allocated as part of our RAM memory within the device. And this memory segment will be used across our embedded software to allocate buffers and save certain content and data within those buffers. And later on, we can free and deallocate those buffers from our heap memory segment. This allocation and deallocation of those different buffers within our heap memory segment will be managed through what is called heap allocators. In C programming, we'll have a set of predefined heap allocator functions within the standard C library. Beside those predefined functions, we can have custom heap allocator functions, like the case of the heap allocator functions within the real-time operating system software. The heap memory segment will have a fixed size that will be provided in general by the linker script. Finally, what is special about the heap memory segment is that the allocation of the different buffers within this heap memory is done at runtime via the different heap allocator functions. Those are the main C-based functions that allow the allocation and deallocation of different buffers and bytes within the heap memory area. So Malloc, this is a standard C function, part of the standard C library, that allow the allocation of set of bytes within the heap memory. The amount of bytes to be allocated within our heap memory will be specified by this input parameter. If we want to allocate space within our heap memory based on the number of elements, then we can use this calloc C function. So this function will allocate the size of each element times the total number of elements to be allocated within the heap. So n times size will define the total amount of memory area to be allocated within our heap segment. Realloc, on the other hand, will take a already allocated area or buffer within our heap segment and then redefine basically the size of the already allocated section. So here we are changing the size of an existing allocation. Finally, if we are done from those allocated buffers and arrays within the heap memory, then we can free the space within the heap memory so that it can be utilized later on by another allocation. Here, whenever we are doing malloc, calloc, or realloc, we'll get always a pointer that will be pointing to a memory area within the heap. And this pointer will be used to save data and content within the allocated segment or section within our heap memory. So this pointer will be always pointing to the start address of the allocated section within our heap memory. In terms of usage, the heap will offer certain benefits and pros in respect to other memory model allocation like stack. The heap will offer kind of flexibility when it comes to memory usage. So we'll not have all the time a fixed memory size allocated to our software. The allocation of the different memory sections within the heap will depend from the workload and the need of our software. The heap does support as well a dynamic data structure allocation. This means that we can, at runtime, allocate sections within our heap for the different data type structures like list or linked list, double linked list, queues, trees, and so on. Also, the heap will offer better RAM utilization in modular systems. Modular systems means our software-based system will consist of a set of modular software entities. Each of those entities will require, of course, a dedicated memory segment for the different variables and data structures allocation. Hence, instead of fixing the memory segment to be allocated to each of those modules, we can just rely on the heap allocation to alloc based on the workload and the need the different memory sections needed by those modules from the heap memory. So the allocation will be here dynamic and not static or fixed. The heap will help, of course, to reduce the load and the pressure on the stack utilization. Hence, we can offload part of the variables and buffer allocation from the stack to the heap. And of course, this is to be done at runtime. And finally, the heap will allow better handling of the different buffer and variables allocation workload. This means it depends really from the spikes that we are getting within our software utilization. If we need more space for arrays, data structures, and variables, then the heap memory will provide this flexible interface that allow a runtime allocation for those buffers and data structures based on the need. So more allocation we need, more heap we'll need. Less allocation is needed, more space in the heap memory will be available for further allocation. On an ARM-based system, the heap will be growing upward. So it will be growing from low address to high address. Of course, this allocation direction, this is managed by the software, which is the opposite case from the stack. The stack on an ARM-based system will be growing from the top or high address to low address. And this growing direction is handled by hardware. Of course, we'll have a risk of collision. And if this happens, then we may get undefined behavior. Undefined behavior means we may have kind of stack overflow, or some data within the heap will be overwritten by the stack. And if this happens, this will be propagated at certain point to our software, and of course we may get hard fault or random crashes. Now, in terms of cons and drawback of the heap usage, one of the major drawback of the heap memory allocation is the unpredictable timing and overhead latency. The allocation of any bytes data or data structures within the heap memory will be done at runtime and requires set of C APIs to allocate, then free those data structures and bytes within the heap memory. The user of those C functions APIs to maintain this allocation and the deallocation of the different sections within our heap memory will introduce, of course, certain overhead and unpredictable timing, especially if this is associated with cache memory. If we have cache enabled and then we use this runtime allocation via heap memory allocation, then this may lead to unstable system when it comes to predictable timing and latency overhead. Another drawback of the heap allocation is the risk of fragmentation. Fragmentation means we'll have kind of free bubbles in between the different allocated sections within our heap memory, like this model or example. Here we have an array of bytes. This is free. Then small bytes allocated here. Then this is free. Then we have bigger chunk of bytes allocated here, and so on. The problem, as you can see, we have set of free bubbles that are not used within the heap memory. And if we try to allocate big chunk of area within the heap memory, then we cannot have a continuous set of free space within the heap memory, because the whole space is fragmented between those free sections. And hence the allocation of this new big section within our heap memory will fail, simply not because we don't have enough space, but because we don't have enough continuous space that match the required allocation. We'll have as well the risk of memory leaks, especially if we are going out of the heap memory boundary. With that, then we are risking to expose set of data and variables outside the boundary of our heap. This will introduce, of course, the heap corruption bugs. Heap corruption bugs means the content of the heap will be corrupted due to the heap area overflow, so going out of the boundary of the heap, or because we are having a lot of fragmentation that may lead at certain moment to corrupt certain bytes here or there. Finally, we'll have what is called out-of-memory failure and at runtime. This is again due to the overflow of our heap memory and going out of the boundary of the predefined heap memory size. This is an example written in C to demonstrate how we can allocate bytes within our heap memory. C define set of APIs and functions within the standard C library to allocate any free space within the heap memory. Malloc, as discussed before, will allocate set of bytes based on this predefined size as input parameter within the heap memory. And then it will return a pointer that will be pointing to the start address of the section allocated within the heap. In the other hand, free will deallocate this space, and hence, instead of having this space reserved based on previous allocation, it will be free and will not have this pointer anymore, let's say pointing to this area, and hence it can be used later on for a new allocation. As you can see, this is the direction of the heap growing within an ARM-based system. So it will grow from low address range to high address range. And this is the exact opposite direction of the growth of our stack memory, which will grow from high addresses to lower addresses. As you can see in this example, the different local variables as well as the input parameters of our C functions will be allocated within the stack memory. On the other hand, the heap memory is reserved for the runtime allocation via those predefined C functions and APIs. Another concrete example where the heap memory is playing a big role to maintain our system running in proper state is the usage of the heap within a real-time operating system software. Example of those real-time operating systems will be the free RTOS. The free RTOS will not use the predefined C functions and API for runtime allocation like Malloc or free. Actually, the free RTOS will have its own heap memory, and it will have its own functions and APIs to allocate space within this custom heap memory. The concept is the same, but the set of the APIs and the way this heap memory is allocated is slightly different from the standard C programming way. The FreeRTOS heap memory will be used in general to allocate space at runtime to the different queues, semaphores, and tasks control blocks. The configuration of this FreeRTOS custom heap memory will be done in general via this FreeRTOS config file. So this will not be exported from the Linka script. Actually, it will be defined and exported via this config header file. The FreeRTOS will have more strict scheme to control basically the allocation of space within the heap memory. So if the allocation will fail, then the FreeRTOS will have a fallback default function or hook function to detect such failure. And hence the user will be able to trap right away any failures when it's come to the heap or heap allocation and deallocation. And this is of course much more robust in terms of heap memory management compared to the standard way of heap allocation and deallocation within a standard C program. So this is our STM32 based project, which will be used to demonstrate the different concepts that we have learned across the different slides. This project is a makefile based one. So this main makefile will consist of set of rules used to compile the different C sources, then will be used to generate the different object files, which will be linked to generate the final ELF image, which will be loaded into our STM32 microcontroller device. The toolchain and the compiler to be used will be the ARM GCC compiler. And here we'll have the set of compiler flags and linker flags needed to compile properly the different C sources for our ARM-based platform. So here we are talking about cross-compilation for ARM platforms. Beside the makefile, we'll have set of sources that will handle the booting of our STM32 microcontroller, as well as the execution of our heap-based example. So in this startup file, we'll have the vector table, and this one will be fetched after power on reset. The first element within the vector table will be loaded into the stack pointer of the processor, and the second element within this table will be loaded within the program counter. Hence, we'll be executing the reset ISR function within this file. And as you can see, this one will be used to initialize the different global variables, and finally jumping to our main function. This main will jump to our example number specified during the build time, and the example itself will be located here. So we'll have a basic example to show up how we can allocate space within our heap memory. So we'll invoke this Malloc function to allocate this buffer size within our heap memory. Then we'll double check that the allocation has been done without problems, and then we'll try to initialize the space that has been allocated, and finally we'll free this space from the heap memory area. Those different mallocs and free functions that are used to allocate space within the heap memory and free it will be defined as part of this heap driver. So here we'll not be using the standard C malloc and free functions. Actually, we have defined our custom malloc and free functions, as you can see. Now, to allocate a heap memory segment to our embedded system project, we'll need first of all to allocate this region through our link script. The link script is just a representation of the supported memory regions layout by our STM32 microcontroller. So we need to specify the different memory regions supported by our device, and besides specifying those memory regions within our link script, we will need to indicate the start address as well as the size of each one of those regions. The heap is just a software concept, and hence we'll need to allocate and reserve space within one of those memory regions to our heap data structure. Because we are going to write and read at runtime to and from this heap memory segment, it should be allocated in a memory region that we can write and read from it. And the ideal target for such memory region will be the RAM memory region. Now here, as you can see, I have allocated the section within the RAM region, and this section will contain basically our heap memory segment. The size of this heap memory segment is specified here, so 8 kilobyte. So this is the max size of our heap memory segment within this project. And of course, I will need to export the start address and the end address of our heap memory segment. Those two symbols will be imported by our heap driver, as you can see, and based on the start address and the end address of the heap, we'll be able to allocate space within this heap memory segment. Here, the start and the end symbol imported from the Linka script will be used by our heap driver to recognize the limits of our heap memory segment. So, thanks to those two symbols, we'll be able to know the start address and the limit address of the heap memory segment to be used here. As you can see, here we are having the C implementation of the Malloc and free heap API needed for this heap memory segment management. The Malloc function will allocate space within our heap memory segment based on the size input parameter. So the size of the space to be allocated within our heap memory segment will be provided as input parameter to our Malloc function. And this function will return a pointer pointing to the start address of this allocated space. The space to be allocated must be always aligned. Means we want always to avoid the case where we are returning an unaligned pointer to a platform that doesn't support unaligned access. For example, if we are going to deploy this function within an ARM Cortex-M0 or M1, then we allow providing unaligned pointer, then we are risking to perform unaligned access to a memory region. And the M0 and M1 does not support unaligned access. Hence, we'll end up by having a hard fault. So, to be in the safe zone, we need to enforce that the space to be allocated within our heap memory must be always aligned. And here, we are enforcing the alignment to be 8 bytes. So this function here is just for enforcing this alignment for 8 bytes. This sbreak function is used mainly to allocate the pointer or the start address of the space to be allocated within our heap memory. So we'll have kind of heap cursor that will be pointing to the latest allocated space area. So it will be pointing to the latest allocated space and the start address of the free space within our heap memory. So whenever we are allocating space, then this one will be incremented to point to the next available area within our heap memory. So if this one was never allocated or initialized, then of course it will be initialized to the start address of our heap memory. Then here we are going to pick up the current heap cursor and then increment it by the size to be allocated. So this one will take as input parameter the size of the space to be allocated, but of course it must be aligned to 8 bytes, so it must be a multiple of 8. So we add the current heap cursor, which is pointing to the next free space within our heap memory by the amount of size that we want to allocate. And again, we need to enforce the 8 bytes alignment. This will give us a pointer that will be pointing basically to the next free space within our heap memory. What will be returned as a result out of this function will be this previous pointer, and this one will be pointing to the start address of the space to be allocated, and this one will be pointing to the next free space within our heap memory. So this one is the result to be returned, and this one will be used later on to point to the next available space within the heap memory. And hence, this heap cursor will be always updating with the next available address within the heap. Once we are done from the allocation of the space, as well as updating the heap cursor, we're gonna return this start address of the allocated space to our malloc function. And this one will do a minimal cross-check to verify that this is a valid pointer. Then it will return it as a result. The free function in the other side is not doing anything right now. So as you can see, it is empty, because there is no need really basically to deallocate already allocated space on an embedded device. And the space that has been already allocated can be revoked and take it again after reset. So on an embedded device, ideally, we can take over basically the different space that has been allocated within our heap memory after power on reset. If not, then we'll need to implement kind of sophisticated logic to track basically what has been already allocated. So we need to have a more sophisticated malloc function that will store more metadata to index what has been allocated and what is free right now. And then the free function needs to grab this metadata, then does certain pointers update to revoke and allocate again what has been already allocated. To compile and build this project, we will need first of all to open a Windows command line, then invoke this build command. This one will invoke the main command, then specifying the example number to be compiled, and then the makefile goal or target. So this one will compile the different C sources to generate the different objects, and then link the objects to generate the final image, which will be loaded into our target device. So build directory has been created, and this is the image to be loaded. Those are the object files, And this is a cal project that will be used to load the binary and flash it into the STM32 microcontroller, then starting a debug session to observe how the malloc function is working. So here I have already connected an STM32 microcontroller and I performed a flashing. So the binary has been loaded into the flash memory. Here I can start a debug session. Then I will be jumping to our main function. Then if I single step, I will be in our example. Here I am trying to allocate a space within our heap memory. And the size of the space will be 5 bytes. After doing the allocation, then this malloc function will return a pointer pointing to the start address of the allocated space. Right now, I will try to check that this is a valid pointer and can be used as placeholder for the different data to be stored. So let's check at assembly level what's happening. So here I'm trying to compare the content of the R3 register against 0. So this C comparison will be translated at assembly level to this line. So the R3 register will be containing the value of the returned pointer out of our malloc function. And here we go. So our returned pointer will have this address 20,000,008. Obviously this is 8 bytes aligned, as you can see, and it is a valid memory region. So I move. Now I am going to initialize basically this heap space. So if I open memory window, then try to observe the content of this allocated space, then see what's going on. Here we go. This has been already initialized with this data. So as you can see, guys, heap is more about providing the flexibility and the ability to allocate memory space at runtime from software point of view. So here we are unblocking our software to get enough memory from this heap memory. And then we need, of course, to have a software logic to maintain this heap memory segment. And this is done via those malloc and free C APIs and functions.